Okay, lecture 1 for Chem 1180. This is the first time I've made up video lectures for Chem 1180. I've done it for my other courses for 8 years. The reason I've kind of been holding back on this is because the calculations that we do are very involved and they take a long time to do, and it's just tough to put on paper like this, but I think I've got it figured out after so many years of doing these other types of shorter calculations in other classes, so we'll give it a try. Now what I do normally is I put in the terms from the book that are important for you to know. I don't define them here because that's in your book. There's nothing to be done but just memorize them. You need to know these terms if you're going to talk about this type of chemistry. And then I go directly into the problems that are very much like those that you'd have on the exam. Now, someone else may be using these videos, but if this is my class, this is going to be the first problem on exam 1, always. And this is what I need you to do. Is the four factors. The first one is concentration of reactants. I need you to write it like that. If you put concentration, that's wrong. If you put reactants, that's wrong. Concentration of reactants. We're past the 1050 stuff, past the 1170 stuff. Now, this is the springboard into the more advanced courses. You need to have an eye for detail. And when your instructor says to get full points to write concentration of reactants, and he's the one writing the exam, you should probably do it. And I'm not doing it just as a show of power where you do what I say. It has to be done this way. It's concentration of reactants. Why is it not just reactants? Well, that doesn't tell us anything. It doesn't tell us, certainly if we have reactants, we know the reaction is going to happen, but it's the concentration that dictates how fast. Concentration is moles per liter. So the higher the concentration is, the more molecules that you have present in the same volume, or ions, or whatever you're dealing with. So in the same volume, you have a higher number in the same volume, so they're closer together. So it takes a shorter period of time for them to meet up and react. So as the concentration goes up, generally the reaction rate goes up. It can go the other way, but it's very rare. So, but concentration of reactants is the first one. Concentration of, I don't know if they say catalyst or a catalyst. They just say of catalyst. So a catalyst, we know, speeds up a reaction. The more of the catalyst you have, the faster the reaction is going to go. And that's all we need to say here. Yeah, we'll talk about each of these in detail later on as we go through this couple of chapters, but that cover this material. Temperature. And temperature is fine. You can say temperature of the reaction. But temperature says all that we need to know there. When you say temperature, generally you can't make one reactant or one product hotter than the other. So temperature just says means temperature of the system. That's fine. Surface area of a solid reactant or catalyst. And this is where people put in surface area, and they leave it like that. That's wrong. They put in area of a reactant. Wrong. It has to be surface area of a solid reactant or catalyst. Now, what's happening there, let's say you have a block of a reactant, a cube, and it's 1 centimeter on a side. Well, each face is going to be 1 centimeter squared, and there's 6 faces, so the total area, surface area, is going to be 6 centimeters squared. Now, and nothing inside the bulk, nothing inside is going to react because the other reactants can't reach it. It has to react off this surface. That's why when you have a reactant that's a solid, generally the reaction goes fairly slowly because you can only react at the surface. Now, what if we cut this cube in half? So that's all we've done. We just split it in half into 2 rectanguloids, I guess. You still have your 6 centimeters from before, but now you have these 2 faces that are open. And each of those faces is going to be 1 centimeter squared. So you're going to have 6 plus 2, so 8 centimeters squared. So by cutting this cube in half, we've increased the surface area by 2 centimeters squared. You cut it in half again, surface area goes up. If you pulverize it, turn it into tiny bits that are 1 micron on a side, you can actually increase the surface area by hundreds of thousands, even millions of times. So the reaction, so all that reactant is ready to go now. It's open to react, and so the reaction rate should go up. So those are the 4 factors. You don't have to explain all of this stuff on the exam. You're just going to have to list these off as written here. I for detail. That's the really big key here. This is the step. And some students, they're not sure why they're taking 1180. At Macomb, we said they have to before they take organic. If you don't, there's some schools where you don't, you miss out on kind of a step in your maturity as a science student, as a chemistry student. And you're also dealing with, this is actually a survey of all the chemistry. So it's a really good course, but it hones your skills and gives you a chance to work on some very tricky problems and ones that you see in real life. It's very rare in real life where somebody has to determine the density, where we have D equals M over V. You're not likely to be in a lab and say, we need to determine the density of this. Measure each edge of this block. It doesn't happen. 1170 is kind of are just the tools that we need to work on real problems. These calculations we do are real life problems. Now everything's computerized, everything's already taken care of in these analytical machines, but they're based on these calculations we're going to be doing. So it's real stuff. It's good. Good stuff. Okay, so 2, consider this reaction. And then write the rate of reaction with respect to methane. Now, the rate of reaction with respect to methane is going to be the change in the concentration of methane over the change in time. And you can see that's going to give us units of moles per liter per second, or molars per second. Get used to seeing these 2 forms of, these are the same thing. It's the change in concentration with time. So the rate of reaction with respect to methane is, it has to be this capital delta. That means change. Square brackets for concentration. If you do this, I see this all the time. There we go. Wrong. I see this. Wrong. And this is 1050 kind of thinking. Not putting the 1050s down. It's that they're just starting out and they think this looks pretty close. We're talking about I for detail. I'm going to keep mentioning this. It has to, and I see things where and people put in this, or T, maybe there's a delta there. No, delta, change in concentration. What you have to always be thinking of is when you're writing something down, you're writing it for another scientist, and it has to be right because they might not understand the context. They might not know what you're doing. They might just see this term. If they see this term, then they know exactly. They say, oh, that's a rate law, or that's a rate of reaction that will help us determine the rate law of this reaction. They can see that. They can see what you can do with it. They know. Has to be like that. So, rate of reaction with respect to fluorine. Change in the concentration of fluorine over the change in time. Rate of reaction of carbon tetrafluoride. Change in the concentration of carbon tetrafluoride. Oh wow, this does seem easy, and this is nice. It is, because we're with respect to each individual species. We haven't tried to compare them. We're not doing anything with them. But that's definitely true. The rate of reaction with respect to only this CF4 is its change in concentration with time. The rate law with respect to hydrogen. Now this is what gets students, because they can do that makes sense, that's easy, but it's when we start comparing them that we have some trouble, and also when we start to do the calculations that are involved. So this seems simple, and it is. When you're just dealing with one species and you want to know the rate of reaction, and sometimes you'll have the rate of reaction for methane, and then for hydrogen, since it's a product, you might have the rate of production of hydrogen. If it's a species that is decomposing, they'll say the rate of decomposition, that kind of thing. But when they say rate, they're talking about either the rate of it being used up or being produced. Okay, now Let's do something with it. So that's a nice simple start, but now we have to use it. Consider the data taken from an experiment involving the above reaction. So that reaction that we had, you can go back if you need to. Actually, I can write it up here. Not that we really need it at this point, but just so that you remember. Now we have this chart. Looks pretty daunting, but we have the time in seconds, and it's all takes place in a half a second. We have the methane. This is in moles per liter. Concentration is always moles per liter. If you see the square brackets, moles per liter. But I put the units in here so you can see that. And you can see the methane starts out 6 moles per liter. After a tenth of a second, it's down to 4 moles per liter. After 20 seconds, 2.2 seconds, it's down to 3 moles per liter. You can see that it's dropping. The fluorine is dropping. And you can see that fluorine is dropping at twice the rate, and it should, because our reaction is 1 to 2. I put in nice numbers. So we have 6 moles per liter of methane, 12 moles per liter of fluorine. When the methane drops by 2 moles per liter, the fluorine drops by 4 moles. This drops by 3 moles from 0 seconds to 0.2. It drops by 6 moles. It has to, because that's what the stoichiometry of the equation tells us. Now the CF4 and the hydrogen start out at 0. There's nothing present. That's usually the case where we don't have any products to begin with. Now as the methane drops away, the CF4 increases. So this drops by 2, this increases by 2, and it should, because we have it's 1 to 1. The ratio is 1 to 1. The methane, or the hydrogen, increases twice as fast, and it should. It's 1 to 2. So just looking at the stoichiometry of the reaction, looking at the coefficients, we can determine, actually just from, if we know these starting numbers, and I give you this chart here, or this column, you should be able to fill in the others if you had to. That's not generally a problem that we do, but you should be able to, just working with the reaction. Now, what is the rate of reaction with respect to methane from 0 seconds? I'm going to have to move it up here. I'll move back and forth to look at that chart. With respect to methane from 0 seconds to 0.1 seconds. Now we said that the rate of reaction of methane is this. Now let's expand this out. We're saying that this is the change of methane. Well, what that is it's the methane. And let me just check your book if they make a different, if they use initial and final, or if they even break it up at all. I don't see it. They just leave it as, oh, I see, okay. So we'll just say at time t minus, I say T2, T1. You can also say methane final minus methane initial, so the initial concentration, either one. And that is what gets a lot of students as we go along too, because it used to be that things are just, D is equal to M over V, that's it. There's more than one way of approaching a problem, or in this case, denoting the terms. So the change in time is going to be T2 minus T1, or T final minus T initial. Means the same thing. But you'll notice that it's always the later time first minus the earlier time. That's because we go forward in time. Now, in some universes, I'm sure they go backwards in time. And then they have to switch these. We don't have to worry about that. This is always going to be the greater time and then the shorter time. So this bottom term is always going to be positive, because this number is always going to be larger than this one. So so what we're looking at, this is T1, make sure I got it on page here, and T2. So put in your numbers. Well, let's do the bottom first. T2 is 0.1 seconds. T1 is 0.0 seconds. That's nice when we start out at 0. Most of the time we do, and then we don't even have to be concerned with this number, because that's always going to be 0. But it doesn't have to be. That's why the next problem I chose it so that it isn't 0. And that's what I'm going to try to do, give you as many different forms of the problem as possible. And so that a lot of times the professor does the easiest one and leaves the tougher ones for the students. So I try to do every possibility if I can. Now the final, the we have 0.1 seconds. What is the concentration at that time? They have to match up. So we go back up here. The concentration for methane at 0.1 is 4 molars. And you want to carry the units through. This is something that a lot of students they never got into the habit. You got to do that. And then we have the units will really save you, and then 0 seconds. 6 molar here. The units will really save you if you mess up. If you don't have the units in there, and let's say you mixed up those numbers, you have them flip-flopped, and you don't have any units of measure in there, how are you going to tell that you made a mistake? So 4 minus 6, that's 2. You can see it's going to be a negative term. And then this is 0.1 seconds. So this comes up to be, and let me just say, in 1180, I assume that you have the rounding down, that you know how to round, you know how to find significant figures. So normally, let me go back up here, I give you 3 significant figures, you give me 3 back. And you say, well, I like to follow those rules exactly, Dr. Champagne. Feel free. In this case, I'll normally give you 3 significant figures. Go through all the twists and turns. Sometimes we're going to see here we have division and subtraction. That's up to you if you want to follow the rules for subtraction and then the rules for division. You're probably going to end up with the same significant figures. Even if you don't, 3 is fine. But I leave that to you. Sometimes it's a tricky concept for students, but this doesn't look too bad, but wait until we get to a problem that has 20 steps, and we do get to those. And each step is either addition, subtraction, multiplication, or division. If you want to keep track of them all the way through, that's fine, but what I do is I give you 3 significant figures to start, you give me 3 at the end, everybody's happy. But I leave that to you. If that is troublesome for you, carry out every set of, or find the significant figures at every step, and that is fine. Most likely you'll come up with the same exact answer. And now the thing here is that we have a negative term, and that tells us something. That means that the concentration is dropping, and that means it's a reactant. So you see that negative sign, that tells you you're dealing with a reactant. Now we have and then we have molars per second, and that's what it should be for the rate. That is the rate, units for rate. No matter what the rate is, it's going to be moles per liter per second, or molars per second. And let's try this one really quickly. What is the rate of reaction with respect to methane from 0.1 seconds? And again, we should have 3 significant figures, so we'll have 3 at the end. And so same thing. We have methane. I'm just going to say final and initial. Make it easy. T final minus T initial. Sometimes you'll see this as T. For the final, there's say time T, and then this will be 0 for initial. But in this case, we're not starting out at 0 seconds, though it is very common to do so. So let me write it down. I'm going to put it over here. All right, now we have T final is 0.2 seconds. T initial, 0.1. And so we go up to 0.2 is 3 molars. 0.1 is 4 molars. And, to make our lives easier, I made that change of significant figures. And I'll do that throughout. I'm not going to really apologize for that. It's okay to do that as long as you keep track. These minor little changes. I'm not stopping the video for for something like that, just like I wouldn't in class. I have to make some of these changes sometime. I'm going to bring this down, minus. And that's really why what has stopped me with the videos over the years is I don't want to be too, be halfway through a problem, realize that you have to make a little adjustment, but that's what we're going to be doing. No big deal. Now, we don't have a lot of time. I want to keep it under 20 minutes here, but notice the reaction rate has dropped. It goes from 20 to minus 20 molars per second to minus 10 molars per second. That does happen. That will happen as the reaction goes along. The reaction rate for with respect to a reactant is going to drop. And we'll stop there.